Hello, everyone. I apologize that I can't be with you today, but I have a commitment at the state capitol that I had to fulfill. So I apologize that I've missed the last few lectures, but I know Larissa's done a great job, and I've gone over the material with her, gave her some talking points and stuff for the PowerPoint slides. So I think everything is really in good shape there. So I appreciate her good work. A couple of housekeeping items here before we jump into the last unit of the semester on tornadoes. Recall that our exam, final exam, which is comprehensive, is Wednesday, May 10th, and that means that we need to have a review session on the Friday, this coming Friday the 5th, or Saturday the 6th. So please be thinking about that, and we'll make that decision in class on Thursday. But please be thinking about what date is best for you. I will send around a study guide for the final exam as I have previously, and we'll go ahead and go over the second exam, all the exams that we've taken, of course, and the problem sets and so on, and make sure that you feel solid about the material. So be thinking about that. Also, the class evaluation, very, very important. You've received the message from the eValuate team at the university, and so please do take time to fill out that survey that describes the course and get your input on it. I'm especially interested in the comments that you have in the written dialogue box. Very, very important for me. I look at those carefully each time and make adjustments to the course accordingly. So again, be thinking about the date for the exam review, May 5th or 6th. I will send a review guide and then also the class evaluation. So let's go ahead and jump into the last section here of the course on tornadoes. Not exactly a mesoscale phenomenon, of course. We're really down at the storm scale. But we put it in this class because it really does fit within the broader context of mesoscale weather, lines, supercell storms, and things like that. So the formal definition of a tornado, a rotating column of air in contact with the ground, the surface. Very important caveat there that distinguishes a funnel from a tornado. It's pendant from a cumuliform cumulonimbus cloud, and it's often visible as a funnel cloud or circulating debris dust at the ground. This is from the AMS glossary. The important thing here is that oftentimes you don't see the funnel, the so-called condensation funnel, and we'll talk about why that exists, why sometimes you see it and why you don't see it. But it's important to recognize that a tornado can be on the ground producing damage and swirling up dust at the ground without a visible connection between the cloud base and the ground. Two principal types of tornadoes. The first one is supercellular, which always occur within a mesocyclone. Again, not all supercells produce tornadoes, but those that do are a particular genre of tornadoes and particular set of dynamics that we'll look at. The second type is a broader category of non-supercell tornadoes that are not associated with a mesocyclone. These can take the various forms of gustnadoes, tornadoes from lines, water spouts, which are essentially tornadoes over water, but the bottom line common denominator is that they occur from storms that are non-supercellular in structure. It's important to realize that tornadoes, of course, are part of a broader category of tropospheric vortices like dust devils and fire whirls and things like that. But we're, of course, talking about deep convection and other types of tornadoes that are produced within convective clouds. Tornado characteristics, it's good to look at some statistics. Of course, they occur worldwide, but 75% occur in the U.S. On average, tornadoes typically don't last very long. The ones that are noteworthy and newsworthy, get a lot of press, of course, last a long time and do a lot of damage. But there's a lot of tornadoes in the U.S., for example, every year, several hundred tornadoes, and most of the time they last only a few minutes. You can look at the average diameter, about a half a kilometer or so, average path length, not very long, less than 5 miles. They can travel quite rapidly at speeds of 60 miles an hour. Of course, they're moving really with the speed of the storm. And in the early parts of the spring, late April, early May, storms tend to move much faster in our part of the country because the jet stream is so strong. The average speed is much lower. As you see there, the next to last bullet, most of the tornadoes in the northern hemisphere rotate counterclockwise. That is an indirect effect of the Coriolis force on the rotation of the parent updraft. Now, we now know why updrafts rotate cyclonically due to the helicity, due to the streamwise vorticity. And we looked at all of that. Larissa talked about that. And so it's really the hodograph structure that controls the rotation of the storms. not the Coriolis force directly on the rotating fluid itself. It's really more on the environment. Of course, wind speeds can vary dramatically in tornadoes up to on the order of 300 miles an hour. It's good to look at tornado statistics. We are sort of the center of the universe for tornadoes here. You look at Tornado Alley. It's hard to see an alley here. It almost goes from the Dakotas down to the Gulf Coast and sort of a secondary maximum from Oklahoma and Texas up through the Ohio Valley, which has been the traditional tornado alley. You all are aware, I think, that Vortex Southeast is underway. It's important to not neglect the southeast part of the U.S. Because there are a fair number of tornadoes that occur there every year. And certainly recently, places like Tuscaloosa, Alabama, that had some very strong tornadoes. You see those a lot. So we are focusing on that region of the country. Average annual number of tornadoes, you can just look at the map here. Of course, the larger the area, the larger the number. Typically, Kansas, Oklahoma, Texas has, in an absolute sense, the largest number of tornadoes. But again, every state in the union, including California, including Maine, including Washington State, has had tornadoes. On average, as you see down there, we have about 1,200 tornadoes in the United States, and it fluctuates quite a bit year to year. And I think I have a graph there. Here you see the annual count of EF1 tornadoes. So these are the weakest tornadoes. We'll talk about the EF scale here. This is a 60-year period. You can see that the number fluctuates quite dramatically from about 350 up to of order 900. And as we know, the weaker tornadoes are the most common, so that's why you see the larger numbers here. Tornado statistics by month, of course, May and June. This is now across the United States over about a 20-year period or so. They occur during the warmest months of the year, but again, you see them year-round. The number there in May, on average, is about 280 or so tornadoes. At the time of day, we looked at this when we talked about the linear storms, quasi-linear convective systems, and tornadoes coming out of those. But local time of day, of course, maximum from about 4 to 7 p.m., time of maximum daytime heating. You see a somewhat somewhat of a maximum around midnight or so. But remember, the quasi-linear convective systems had the much more pronounced secondary max in the early hours of the morning, whereas the overall more isolated tornadoes, the supercell type storms, tend to occur. The ones not in lines tend to occur most frequently in the late afternoon hours. Weather fatalities. As meteorologists, it's important for you to know that more people are killed by floods than tornadoes. You see heat waves as well. Looking at the various averages, especially the 10 and 30-year averages. I actually misspoke there. I was looking at the red bar. In terms of the 10-year and 30-year averages, heat really kills people more than anything. And then tornadoes and, of course, flood deaths are prominent as well. And hurricanes, their infrequency is part of the reason why the death count is so low there. So it's kind of important to know. Most people would think that, well, tornadoes are the biggest killer. Yeah, that's not untrue, but on the long-term average, heat actually is the bigger killer than tornadoes, followed by floods. Tornado fatalities. You look at this, of course, there are some years where we have big tornado outbreaks, like 1974, the super outbreak. And then, of course, in 2013, I think it was, 2012, 2013, a larger number of people died in tornadoes, comparatively speaking, for, say, the last 30 or 40 years. So you have these big outbreaks, and they do produce a large number of deaths. Of course, we're working hard to try to get the fatality count down as much as possible. Looking at the tornado deaths, of course, you look at the impact of technology like forecast models and better understanding of the atmosphere. You look at things like radars and a better communication system and so on. The tornado death rate has been declining, so that's important. If you look at the number of tornadoes reported, obviously people with cell phones and the more dense population that we have now in the U.S., the tornado counts are, of course, affected by those things. And so you have to distinguish between the actual physical increase in the number of tornadoes versus the increase of the number of reported tornadoes, because people are seeing more of them just because there are more people in the U.S., for example, and they have better capability of communicating whether or not it was an actual tornado with cell phones and things like that. So we are making good progress, clearly, but people still die, obviously. Of course, a notable local event that we had here, the big May 3rd outbreak of 1999, produced a very long track F5 tornado that ripped through more, and that's obviously gotten a lot of attention. I believe there were, let's see, what does it say, number of tornadoes? There were 58 tornadoes in Oklahoma. I think there were on the order of 45 people killed in that outbreak, and there was an estimate that there could have been, upwards of several hundred fatalities had it not been for the advanced technology and other things that we have today that weren't present, for example, 40 or 50 years ago. And there you see some of the devastation on I-35, just west of I-35. If you're familiar with the Baptist Church in Moore up there, First Baptist Church. If you look around to the left there to the west, you see that tornado. Of course, this thing is being studied, has been studied. I mentioned it a lot in the context of horizontal convective rolls, that particular storm was thought to have been initiated by horizontal convective rolls in the boundary layer. What's very interesting about being in Oklahoma is the very first tornado forecast was actually performed at Tinker Air Force Base back in the late 40s. And if you've heard the names Fawbush and Miller, they were the ones responsible for these various, called the Miller diagrams or the Fawbush and Miller diagrams, these hand analyses. And I think I showed you a couple earlier that had all kinds of different line styles and colors and things like that. And they also, I believe, wrote some really terrific things in the Air Force, terrific documents for forecasting tornadoes. But this first case, there's, as the story goes, the general was telling them, what's going to happen here, and they went out on a limb and said, the conditions look to be right for a tornado, and in fact, a tornado did occur. And then a week later, that same sort of thing happened again. So there's a monument actually at Tinker Air Force Base. You can go visit it, and you can find a lot of information online. But the main point here is that the very first tornado forecast actually occurred here in Oklahoma. So it stands to reason that we are kind of the center of the universe for tornado forecasting. The Fujita scale is something you've heard about, obviously, and very few people know that the Fujita scale concept actually was based on winds that actually go up to and above Mach 1, which is the speed of sound. And in fact, the Fujita scale went from F0 to F12 when it was first devised, because it was filling in the gap between the Beaufort force scale, which was basically had its origins in the maritime usage, ships and things like that to characterize wind. And then the actual, as you see in the lower right there, the Mach number, which is quantified as the ratio between the actual speed of the flow, the speed of the wind, versus the speed of sound. And so Fujita filled in the hole there and said, okay, we need this scale to fill in the holes. And ultimately, it went from basically the highest Beaufort to the low part of the Mach number scale. In reality, of course, winds in the atmosphere do not get up to the speed of sound. They only get up to maybe about 300 miles an hour. So in practice, the early Fujita scale went from F0 to F6. And then it was revised to F5 as being the highest Fujita number. And then the enhanced Fujita scale, the EF scale, came into existence several years ago to really correct it. And of course, the Fujita scale is based entirely on damage, whereas the Saffir-Simpson scale for hurricanes is based on the actual speed of winds and the pressure as determined by aircraft and so on and so forth. This is based only on an after-the-fact assessment of the damage, which of course depends on the quality of structures and so on, so it's very qualitative. And you can look at the enhanced Fujita scale here. I won't go over it in detail, but you ought to read that and be certainly familiar with it as a meteorologist. Looking at all the percentage of tornadoes by Fujita class scale, this is the old Fujita. It's not the EF scale, it's the old Fujita scale. And you can see that about 3/4 of the tornadoes are actually F0 and F1 category. And again, the higher you go on the Fujita scale, the more rare these tornadoes become. And that's something that we saw earlier when we looked at supercell storms. Since the F4 and F5 tornadoes only come out of supercells, then their frequency is certainly tied to the frequency of supercell storms. It's important to note there is an unknown intensity of tornadoes there, that green slice of 3%. So we don't always know what the intensity was. And of course, tornado-related deaths, to the extent that one can do this accurately, as we saw earlier, the supercell tornadoes produce the most damage and the largest number of deaths, even though they are the rarest type of tornado. And then you see there the F0 and F1 produce relatively few deaths, and F2 and F3 produce about a little less than a third. Now, one of the things that we, of course, have learned over the years are the types of environments that are characteristic of producing tornadic storms. And as we talked about earlier, we can measure this in a variety of ways, including the Bulk-Richardson number, which is the ratio, remember, of the cape to the shear in a variety of layers that you might measure, at the 0 to 1 kilometer shear, the 0 to 6 kilometer shear, whatever. And so these are proximity parameters for actual tornadoes. This is out of your book that shows the tornadic storms versus severe storms versus non-severe storms. And you see a massive amount of spread there. And one thing that's important here is to realize that you can have CAPE of, say, on the order of 3,000 to 4,000 joules per kilogram and 0 to 6 kilometer shear that is right in the supercell range and not get a tornadic storm. You could get a severe storm but not a tornadic storm. So this continues to challenge us in terms of understanding why some storms produce tornadoes, why others do not, basically forming in environments that have essentially the same critical parameters to them. In this case, there's looking at the mixed layer lifted condensation level against a low-level shear. You can look at tons and tons of these kinds of parameters, and again, trying to distinguish the preponderance of tornadic versus non-tornadic storms that are, the various environments in which storms tend to form. So you look at the correlation here. That straight line just indicates essentially a demarcation of tornadic versus non-tornadic, but you see a lot of red and blue mixed together, which means, of course, that it's difficult sometimes with the same environments to know which kind of storm you're going to get. I like this plot a lot because it really shows the tornadic environments based upon what we think in terms of cape and shear to be conducive to tornadoes. And you see the big bullseye there in the south central U.S. And if you want to think of Tornado Alley in terms of tornado environments, you see it there very prominently. But it's also important to note that other parts of the world, for example, a very southern part of Brazil and other parts of Asia, have environments that are quite conducive to tornadoes. So let's kind of now, with that background in terms of the climatology, let's look at the life cycle of supercell tornadoes, so-called Type 1 tornadoes. This is a phenomenological approach, basically, started out that way. Again, what I mean by that is it's based on visual observations. And so the first stage that you have typically is a so-called organizing stage, or the funnel stage, where now with Doppler radar and numerical simulation models, we know that we tend to get mid-level rotation in the storm. Recall that mid-level rotation is due to tilting of environmental vorticity. You can get visual evidence of a condensation funnel or at least a strong wall cloud at cloud base, and then a clear slot beginning to develop around the west side of the storm. So if you look at the graph here on the left, you see obviously the warm moist inflow, you see the forward flank downdraft, the rain cooled outflow. The storm here's a bit of a hook echo. The rear flank downdraft that we talked about descending, bringing drier air down, and maybe a push here behind the gust front. And the enhanced inflow is due to the lowering pressure within the mesocyclone that creates a high to low pressure gradient force into the mesocyclone. So at this point, a tornado is not on the ground, but it is in a funnel stage. And one of the things that we're going to talk about shortly is the importance of the downdraft in actually creating the very large tornadoes. Before, we didn't really think that was the case. We thought that it was mostly updraft and stretching, but it turns out that the presence of a downdraft in these supercell types of storms is quite important. The mature stage, now you see the condensation funnel in contact with the ground. Now, the condensation exists here in the funnel because there's low pressure, right? So we know the vortex is a cyclostrophic type vortex, and it has low pressure. So we know that when air rises, if it's moist enough and it rises to lower pressure, it expands and cools. And that expansion, due to the fact that the air is rising to lower pressure, causes the air to cool to its dew point temperature, and then it condenses. Well, the same is true for air flowing horizontally into the vortex, into the tornado vortex. So if it's coming from left to right here, or right to left, as it encounters lower pressure, it condenses. So air rising vertically encounters lower pressure, but air traveling horizontally encounters lower pressure in the vortex. But of course, if the air is not sufficiently moist, you won't get a condensation funnel, and that's why it's called a condensation funnel, in fact. So over here, you see the hook echo developing more prominently, rear flank downdraft clearly evident. That creates this clear slot. If you chase storms, you look to the west, you see this wrapping dry air, clear slot coming around, and you see this essentially an occlusion where the tornado occurs, the occlusion between the rear flank downdraft caused by the gust front here, the rear flank downdraft, the forward flank downdraft, the rain-cooled outflow, and then wrapping back there the tornado. So due to this enhanced convergence from the rear flank downdraft, you get stronger stretching of the vortex, so the tornado spins out. The third stage, and again, very classic sense here, is the so-called dissipation or rope stage, where now what has happened here is the rear flank downdraft causes this mesocyclone back here to occlude. Okay, so essentially this thing becomes rain-wrapped, and a new mesocyclone, and I'll show you this a little bit later on when we talked about cyclic storms, this thing will tend to form out ahead of and to the east of the previous mesocyclone. This is, in some sense, it looks like classic cyclogenesis on the synoptic scale, where you get an occlusion here and then maybe another low forms downstream. In this case, it's really on the storm scale. So this thing, as it occludes and weakens, the tornado tends to rope out. And yet the winds can still be quite strong here because the cross-sectional area of the tornado can be relatively small, and at the vortex intensity, which is the vorticity times the cross-sectional area, if the area goes down, the vorticity goes up. So the vorticity can still be quite intense in the tornado. So it could still be producing substantial damage. Only the most classic supercells tend to go through this, supercell tornadoes tend to go through this three-stage life cycle, especially when you see the roping out stage where you have a very serpentine type vortex. So let's kind of look at this from a point of view of now shift from phenomenological to more a physical dynamical point of view. Of course, as we recall the supercell structure, we have the low-level inflow, we have the flanking line gust front, the rear flank downdraft that we saw here, the hook echo wrapping around, the forward flank downdraft, obviously precipitation, hail, the tornado forming right here at the tip of the hook echo, where we get the strongest tilting of low-level vorticity along the forward flank gust front that Larissa talked to you about, very, very low-level tilting that tilts the vorticity at low levels and can stretch it very dramatically by the intense updraft of the mesocyclone. But again, we'll talk about the role of the downdraft here in just a second. So the real question is, how does a supercell storm, and the low-level rotation that we know that we talked about earlier, that Larissa talked about, it is generated by the tilting of baroclinically generated vorticity along the forward flank gust front. So this diagram here shows it very nicely. Here's the FFD. Here's the gust front right here, this blue scallop line. Here are the vortex lines. And so recall that due to baroclinic effects, we know that there's that rotation within the head of the gust front. So the vorticity, due to baroclinically generated effects here at the gust front, gets tilted at extremely low levels. Okay, but if you think about it, that vorticity, when you tilt it, it's still above the ground level. Okay, even if I have a vortex line that's very close to the ground and I tilt it upward, as I tilt it upward, I'm taking that vortex line lifting it off the ground. So the vortex line is not coming in contact with the ground. So in other words, the real question is, how do we actually get vorticity in contact with the ground? There again is this schematic that shows, as we talked about before, the tilting at low levels. You saw this earlier. And of course, the vorticity as it spins up here creates dynamic pressure force that draws air down from above. That's the rear flank downdraft. And then it also draws air from below into the mesocyclone, which stretches the vorticity from low levels. Okay, and then of course the spreading gust front, as we showed before, initiates a new center of rotation. We'll talk about cyclic storms in a minute. This is what we looked at before. Here's the occluding updraft here. It's still rotating, but the gust front due to the rear flank downdraft is pushed out ahead. This new convergence center out here, due to tilting again of low-level vorticity, creates a new mesocyclone. So it's a cyclic effect that we'll look at again. So tornado genesis. We just looked at and recalled the development of low-level rotation, but ultimately, how does the tornado actually form in the context of that rotation? Because I just told you that even if you tilt vortex lines that are right close to the ground, you tilt them upward, you're taking them away from the ground. You're not bringing them in contact with the ground. So some of the questions that exist: how many different ways do tornadoes form? Is there one principal way, or are there multiple ways? Second bullet, we talked about that earlier. Why do storms essentially in the same environment, one produce a tornado and the other one doesn't? A question that I've always been fascinated by is, why do tornadoes occur? Not how do they occur, but why do they exist? What function do they play in the atmosphere in terms of bringing back equilibrium due to some instability. As we talked about a lot in this class, that the weather itself and other things, there's instability in the atmosphere, and these phenomena exist to get rid of the instability. So what instability is the tornado getting rid of? And certainly, how do large values of vertical vorticity arise at the ground? And as I mentioned, tilting can't explain that because you're lifting the vorticity up, you're not putting it in contact with the ground. So one concept that exists for tornadogenesis is this sort of all-at-once concept, as I like to call it. The NexRad radar data show that about 50% of tornadoes seem to form sort of all at once over the depth of, say, 0 to 2 kilometers. And by that, what we mean is that it's not that you see rotation form in one part of the storm and then appear, say, successively at lower levels. It's essentially where you get a spin up at say, multiple levels from 0 to 2 kilometers simultaneously. Now, this diagram that's taken from a paper by Jeff Trapp, who's now at Illinois, and Davies Jones, who's now retired, shows that if you have convergence that's constant with height, okay, convergence that's constant with height, then a vortex will form as you see below. So the gray arrows indicate air motion, okay, and we have convergence, okay. You see the air coming in from all directions, right to left and left to right. So we've got convergence, converging in here. At time t, you see this big circular vortex. But if convergence is happening basically uniformly with height, then what will happen is this rotation. You see this thing is rotating. You see the little arrows here. Down here, this one little arrow in the biggest vortex. And then as we spin it up, the rotation increases, the area contracts, okay, and the thing deepens. So there's convergence acting on a vortex. It's stretching. If the vorticity is, if the convergence is uniform with height, then you basically get this thing spinning up uniformly with height. It deepens with height. Okay, but the intensity essentially is uniform with height, so the rotation is constant with height. So as you go from t to t plus delta t to t plus 2 delta t, the vortex intensifies uniformly with height. And that's kind of an all-at-once concept of the intensification of low-level vorticity, because notice that the rotation starts here broadly, say within the mesocyclone at low level. So that's one idea. So essentially, this is sort of replaying that high angular momentum air, approaches the axis of rotation faster in the boundary layer because convergence is greater there. Okay, the air is turning in toward the center of the rotation because friction slows it down, and it's not in geostrophic balance, so there's friction there. Friction turns it toward low pressure, so you get convergence, and therefore you get a spin up of vorticity from, as you see there, from left to right. And the rotation is stronger near the ground. Okay, now here's the paradox. When you look visually at tornadoes, and any of you that have watched tornadoes form or seen them on video or whatever, you tend to see this tornado starting at cloud base, as we looked at in the idealized 3-stage model, starting at cloud base and then sort of working its way down, the funnel descending. And you see this a lot. We saw just earlier this year, TV station, it would show a tornado and all of a sudden it's descending and now it's on the ground. So the question is, how does that occur? So there's a theory called the dynamic pipe effect, okay? And here's how the theory goes. We have the same type of diagram that we had before, okay? This is so-called step 1, where you have maximum convergence located aloft, okay, and relatively weak surface inflow. So it's a little bit different than the model we looked at previously. It says, well, the convergence isn't maximum at the surface. You see the inflow here being maximum a little bit higher up. So the initial vortex time is t, okay, and the vortex is deformed by the inflow and the upflow, which are the bold arrows, because the wind is changing with height. We get weak winds down here and strong winds here, so you're going to get a deformation essentially of the vortex. The area, the cross-sectional area, would be smaller up aloft here than it will at the ground because the convergence is not maximum at the ground. It's maximum at some area above the ground. So therefore, the strongest rotation is in fact located aloft, not at the surface, not like what I just showed you for that kind of uniform all-at-once model. Okay, now step 2 is this. It says here, the vortex aloft is cyclostrophically balanced. Okay, if that's the case and there's no instability in the vortex, so flow can't come in through the sides. What is a cyclostrophic vortex? It's one in which the pressure gradient force that is directed inward toward the center of vortex, where there's low at the center, is balanced by the centrifugal force, which is pointed outward. If there's a perfect flow balance, then the flow has no radial component, no component in toward the center or outward away from the center. It's all tangential, so it's all flow that is going in a vertical or swirling motion around the vortex. So nothing can come in through the sides. Now, notice again that there is, of course, low pressure in the center of the vortex. That creates, and we know that there's low pressure, we know that pressure gradient force from high to low accelerates the flow. So this creates essentially a suction from below, okay, that brings air in only from the bottom. So the air that comes in from the bottom, that's the only, can't enter through the side, so it comes in through the bottom. And when it does, it begins swirling. Okay, it goes from a vertical velocity to a tangential velocity, and it also then becomes cyclostrophic. And the idea here is then that as the flow, as you see here, goes upward, okay, and it starts spinning as it enters the bottom part of the vortex, then it becomes cyclostrophic and the vortex builds downward, and this vortex descends with time because the flow is becoming part of the vortex. As it rises, it's not swirling, but as it gets close to the vortex, it then begins swirling cyclonically, becomes balanced cyclostrophically, and the more rising motion you have, the more air that you have starts spinning, and therefore the vortex builds its way down to the ground. Okay, so that's the so-called dynamic pipe effect. Dynamic in the sense it's changing with time. It's due to, to accelerations, and it's a pipe. It's essentially a pipe building its way down from cloud base. So, it's not clear that these theories apply in all cases, and so these were theories that were espoused, as you see, this is back 20 years ago in 1997. But the thing is, they don't account for what's happening in the storm itself. They really focus on the vortex structure and not on the storm structure around it. For example, the clear slot, the hook echo, the thermodynamic structure across the mesocyclone. This is all just pure dynamics, pure cyclostrophic concepts. And there is an observation, of course, that we have that significant tornadoes do not occur in the absence of a downdraft. This is something that we've known for a long time, but we'd sort of dismissed it as being not really relevant. But all of a sudden, the clear slot and the hook echo became more than just passive structures in the storm. They became potentially implicated in the process of tornadogenesis. So let's now put a finer point on what I had mentioned previously, and that is how do you get vorticity down to the ground when it's initially basically zero at the ground. Okay, now we're not talking about gust fronts here. We're just talking about, for example, environmental shear. So no baroclinic generation, no gust fronts. Just suppose that we have a vertical shear profile that creates vorticity, as you see here in this picture. Okay, now if we draw vorticity up in a cloud and we have low-level convergence below, we have rising motion above. Mass continuity tells us that if we have convergence here, flow's not going to go through the ground. The ground is solid and it's horizontal, no terrain. It rises upward, so convergence of rising motion, mass continuity. Look what happens to the vortex lines. The rotation gets tilted vertically. As I mentioned earlier, it gets lifted upward. Well, how do you get it down to the ground? A tornado is vorticity in contact with the ground, right? Clearly the vortex is touching the ground. Well, these vortex lines aren't touching the ground. In fact, as we saw when we looked at the dynamics of supercell storms, we lift these things up. They actually create either sort of low-level rotation or mid-level rotation, but it produces vorticity that's not at the surface. And to have a tornado, that means vorticity at the surface. So this was the dilemma. How do you get the vorticity down at the ground? Well, here is where it was recognized that the downdraft may play a role. Okay, so this diagram here continues, and this is from your book, so please remember to read your book. When there is a downdraft, for example, from the cloud, then it will take the vortex lines and tilt them back downward. The purple shows the downdraft here until the vortex line actually comes in contact with the ground. Okay, now notice here that the vertical vorticity is at the surface. And you see this thing that looks like a tornado because you've now got the vorticity, the vortex line here that was previously tilted upward by the updraft. And now you're taking this vortex line, joining with it. This thing is tilted downward by the downdraft. And you're basically bringing the vorticity down, coupling it with the vorticity that was tilted upward. And so now you have strong vertical vorticity at the surface. So it's believed that this notion of a downdraft is what actually brings vorticity down to the ground. And guess what? The rear flank downdraft is ideally positioned to do that. Okay, the forward flank downdraft, that's out ahead of the storm. The rear flank downdraft is right by the tornado because that's the clear slide is on the back side of the tornado and the hook echo is wrapping around. So if you go back to that earlier figure, you realize this downdraft is ideally positioned to tilt environmental vorticity, not baroclinically generated, environmental vorticity down to the ground. Okay, so this picture, I think it's a very good picture, shows this. You see the rain-free cloud base here. Here's the wall cloud. The forward flank rainy downdraft is off to the right, and here's the clear slide. Okay, it's completely devoid of rain, and if we were, more to the left here, you'd see the hook echo wrapping around, the rain curtain wrapping around from right to left here. But this clear slide is very pronounced. Okay, and so as it says here, a lot of observations have shown that you don't get significant tornadoes, and I want to point that out, that we're not talking about all tornadoes, we're talking about the significant supercell tornadoes unless a downdraft is present. And we've learned from numerical simulation models that some of the air that's actually in the tornado, we can track it back with trajectories in a numerical model, actually passes through the rear flank downdraft. So that really does lend credence to this model that the air that actually makes it into the tornado did not come from low levels, it actually came from mid levels in the rear flank downdraft, and therefore is responsible for bringing the vorticity down to the surface. And so here's a picture of numerical simulation, again from your book, that shows updraft greater than 2 meters per second in pink, downdraft greater than minus 2 meters per second in blue. These are trajectories in the tornado cyclone, essentially, that are tracked backward in time. And notice that although some of them come from the forward flank, air riding over the gust front coming in the mesocyclone, that a lot of these have passed through this blue area, which is the rear flank downdraft. So sure enough, there's evidence to suggest that air in the tornado does not all come from low levels. Some of it comes from above. Okay. Now, numerical simulations have also shown that we get so-called arches in the vortex lines here. One, it says in the tornado, across the rear flank downdraft, not depressed downdraft as in that previous schematic. Okay. So the previous schematic here, this suggests that it's only due to tilting of environmental vorticity due to the shear of the environmental wind. It says right here, assume no low-level baroclinic generation. So again, we're not talking about anything to do with a gust front. Now we're saying, well, wait a second. Numerical simulations show that vortex lines don't behave exactly like what we just saw. There actually is an effect that looks to be baroclinically generated vorticity, and that is because you get this sort of kind of an arch here in the vortex lines that can't be explained by the simple theory we just looked at. Okay, so let's look closely at this figure. The environmental vortex line is being tilted here. Okay, this is due to environmental shear in the standard process that we saw earlier. Okay, so there's cyclonic vorticity due to tilting of the environmental shear. That's the standard process. Here's the RFD, precipitation cascade as it's called. This is a figure again from your book. This whole thing is the wall cloud, so the mesocyclone is right up here. Okay, the wall cloud and the low-level mesocyclone. You see, look at this vortex line, how you have anticyclonic vorticity here and cyclonic vorticity over here in the mesocyclone. So what you find in numerical simulations is these rings of vorticity that are surrounding the low-level downdraft. Now, remember when we had a simple cloud, and I showed you the vorticity, you have a warm updraft in the center of the cloud, and we saw that there was vorticity on either side of the cloud due to baroclinic generation. Okay, if you look carefully here at this downdraft, okay, the air is coming down here, you see the blue arrows, the vorticity has to be such that you get rotation like you see here. Okay, it's downward on the back side of this vortex line and upward on the front side. So this creates essentially a vortex ring, like a smoke ring that is descending and spreading out. Now, as that does so in these steps, then it gets tilted upward to where you get an anticyclonic vortex over here and a cyclonic vortex over here. Now, notice again that the rear flank downdraft is bringing these vortex lines down to the ground because they come right down to the ground because the downdraft brings them down to the surface. Okay, then they get caught up in the updraft of the mesocyclone, and you get the tilting that couples with the environmental vorticity. Okay, so you could look at this specifically where it's purely baroclinic generation of vorticity with no environmental tilting. So in this case, it's a cold downdraft. Here's the downdraft, contains vortex lines as shown. Could be the RFD or the Hooke echo. So here's the downdraft. So it's basically our cloud upside down. Okay, vorticity looks like this. Strong vorticity. Again, go back to our lectures where we looked at a simple cloud where you have vorticity. It's basically a toroidal vortex or like an inner tube with the cloud in the middle. That's how the rotation looks. And notice it's uniform at all levels in a simple schematic because there's downdraft in the middle. Okay. Now, suppose you have environmental flow coming from this direction. Okay. So as it says here, let's assume the ambient flow sweeps vortex rings forward as they are descending. So these things are descending due to the downdraft. Okay. But if you add now an environmental flow component, okay, then it tilts the vortex lines across the updraft downdraft boundary. Okay, so there's updraft over here, the mesocyclone, right? The mesocyclone is here. The rear flank downdraft is here. So these things are getting lifted on the forward edge, descending on this edge, and the environmental flow is advecting them from left to right, as you see there. Okay? Now, continue this process. The updraft just east of the Hooke echo. So here's the updraft I mentioned earlier. Remember I said the updraft is here. Now we're showing it. Here's the updraft. It tilts these vortex lines up very, very strongly. Okay, remember the rear flank downdraft here brings them down to the ground. Then they tilt upward strongly due to the forward flank or due to the mesocyclone. Okay, now remember these are generated baroclinically. They're generated baroclinically in the rear flank downdraft, which is a warm downdraft. So it creates these arches. See these arches right here that straddle the rear flank downdraft. So it says stretching intensifies rotation on the cyclonic side near the mesocyclone, which is this guy right here. Okay, this is anticyclonic. This is cyclonic. We showed exactly that same thing right here. Cyclonic here, anticyclonic here. Cyclonic here, anticyclonic over here. So this effect of the baroclinically generated vorticity in the rear flank downdraft, taking the vorticity down to the ground, getting tilted up by the mesocyclone updraft, and then creating preferentially the rotation that intensifies by stretching on the cyclonic side near the mesocyclone. Okay. Now, the question then is, that's all baroclinic, right, as we've talked about. Now the question is, can you do this without temperature gradients? Because storm intercept vehicles that are driving below mesocyclones across, the forward flank gust front and stuff, when you're looking, well, actually it's more the rear flank downdraft in that area behind the mesocyclone, it shows that there are very few temperature gradients. The temperature gradients are very weak. So then you'd have to argue, well, the baroclinic effects then are not very strong. Okay, so then the question is, well, let's take baroclinicity out of the picture and let's just suppose that we have a barotropic flow. Okay, remember what a barotropic atmosphere is. It says that the temperature is uniform on a constant pressure surface, for example. Okay, so here's a simple experiment that was done by Bob Davies Jones using a numerical model and to look at answering the question, does a purely barotropic mechanism exist? Barotropic mechanism exists to do what? To bring vorticity down to the ground and create spin-up of vorticity that would be characteristic of a tornado. So we argued earlier that an updraft that simply rearranges vortex lines by tilting cannot explain vorticity at the ground, right? That is, environmental vorticity, which is only due to the shear of the environmental winds increasing in speed with height, gets tilted by an updraft. Okay, there's no gust front, there's no baroclinic effects. We showed that vorticity is not at the ground, it's tilted upward. So the question is there a mechanism that doesn't involve temperature gradients that could in fact get the vorticity at the ground? We can't do it by tilting. Is there some other mechanism? So what Bob Davies Jones did here, he said, well, let's think of this. Let's create an axis symmetric model that simulates a mid-level mesocyclone. So we're now talking about how do you get the tornado rotation down to the ground in a purely Beltrami flow. Now remember, what is a Beltrami flow? It's a flow in which the vorticity vector and the velocity vector are everywhere aligned. In other words, it's a flow in which the vorticity is purely streamwise everywhere. Okay, and in your problem set, problem set 5, I think it was the very last problem, I had you work it to where the vorticity omega is equal to lambda times v. Lambda is something called the abnormality. So it's just a proportionality constant to give you the right unit. So omega, that is the 3D vorticity vector, and v, the velocity vector, are essentially parallel everywhere. So the vorticity is everywhere streamwise. So in this simple model, he said, let's impose a cyclonic updraft, you see there in blue with the updraft arrow and the swirling flow, surrounded by an anticyclonic downdraft. So we have updraft here and downdraft around it. Okay, now it turns out that theoretically this is a kind of a classic Beltrami flow. And it also turns out the flow is balanced. So this initial state, if it's specified properly, is steady. It will not change with time unless you impose some type of perturbation. So he's saying, suppose we have essentially a mesocyclone here in the middle, surrounded by a downdraft. It has to be downdraft by mass continuity that's rotating the opposite direction. Okay, and he was then saying, let's simulate tornadogenesis by introducing hydrometeors through the top of this model in a divergent outflow above the updraft. So in other words, he's saying, you know, we know that there are hydrometeors that are produced by the storm, and we know that they fall, and we know that the Hooke echo is an indication of those hydrometeors, precipitation, okay, and they're falling around the updraft, okay, not necessarily symmetrically around the updraft. We know the Hooke echo sometimes will progress around the updraft and the tornado will become rain wrap, but suppose that this is the case. Now the key point here is that because we do not observe baroclinic gradients below the mesocyclone and around the river flank downdraft, he said, suppose that these hydrometeors don't evaporate, okay? Suppose they only create a body force, and by that we mean drag. Suppose they only exert a drag on the air, and there is no evaporation to create temperature gradients, because temperature gradients are observed, so we don't want them in the model. Let's just suppose that these things drag air down, okay? And that so-called rain drag, the loading term that we looked at in the buoyancy term. So as it says here, they fall in the updraft-downdraft interface, simulating what? A rain curtain, or a Hooke echo, on the scale of a Hooke echo, dragging air down with substantial angular momentum. So the point is that these things, they're kind of like a fountain. They here in the updraft, and they come down here and they fall right here on the interface between the updraft and the downdraft. Well, why are we doing that? Well, because that's exactly the Hooke echo. Okay, the Hooke echo wraps around the mesocyclone. The mesocyclone clearly is a region of rising motion. The Hooke echo is, since there's precipitation in it, there's falling, you know, there's descending motion there. So we're interested in this interface between the mesocyclonic updraft and the Hooke echo downdraft associated with it. Okay, so again, rising motion here, sinking motion here. The rain is falling. It's not cooling, not changing the temperature. It's just dragging air down with it. And it's dragging air, as it says, with substantial angular momentum because the air is rotating. Okay, so here's the initial conditions of the model. This is the radial velocity. So the air is blowing in and out. So at low levels it's going in, upper levels it's going out. So convergence, divergence. The axis of rotation of the model is on the left in all these pictures. Okay, so it's axis symmetric. So here's the rotation axis on the left, in, up, and out. So here's V phi. Okay, this is into the page. It shows an arrow into the page, swirling into the page. And the vertical velocity is updraft here and downdraft here. So put the far left and the far right pictures together, you get an in, up, out, and down circuit here like this, okay, for the horizontal and vertical velocity. Then this is V phi, which is the tangential velocity, which is blowing into the page. Okay, notice that the updraft is slightly bigger than the downdraft in size. And the downdraft is rotating anticyclonically because, again, we want the updraft to be cyclonic, the downdraft to be anticyclonic. Again, this is a balanced flow, will not change unless you perturb it somehow. Okay, so this is all a non-dimensional model. So what he did was he ran this to three and a half non-dimensional time units. Okay, and this is slightly different. I'm showing you slightly different stuff than I showed you in the previous picture. Okay, so this is the radial velocity, VR, coming in and going out. Pretty much the same. But here's the vorticity. Okay, notice that you're getting now notice this is the horizontal vorticity, the azimuthal vorticity, eta. Okay, blowing into the page here. Okay, that's a vorticity. And then the vertical velocity, it doesn't look like it's changed a whole lot. Here's the angular momentum, but look at the rain. Okay, there's rain falling. Essentially, here's the updraft and the downdraft. There's the interface. The rain is falling right in the interface, and it's bringing air down with it. Okay, and this is momentum advection, but we won't look at that right now. Here's a little bit later on in time. Notice what happens. You start to get this really strong inflow jet very close to the ground. So the dash contours are right to left. You get strong rising motion. Look at the updraft here and how close to the ground it is. So you get a really strong inflow jet, a very strong updraft. And then the return flow, of course, is stronger here. And you also get a secondary inflow there, and then a downdraft that is strengthening over here. Go a little bit further now, you see a pronounced change. A really, really, really strong low-level jet coming in very, very close to the ground, super strong. With, notice the updraft here, super strong, right close to the ground. So you get this really strong inflow jet, really strong upflow. And notice how the rotation here, the V phi, indicated by the tangential velocity, is now, again, it's a swirling flow. It's the flow into the page is extremely strong, right close to the ground. Okay, so what's happened here? We get a strong inflow jet, we get a strong updraft, and we get very strong vertical vorticity, very strong azimuthal flow, right close to the ground. And this is in the absence of any temperature gradient effects at all. All we're doing is taking angular momentum and bringing it in. And so if you look at the angular momentum here, here's the rain. It's taking this angular momentum, bringing it toward the axis. This is the angular momentum advection. I forget what this parameter is, but anyway, it's spinning up. It's essentially the ice skater analogy, but without any temperature effects at all. Okay, so what happens in this simulation now? Precipitation drags the air down, as we talked about. It has high angular momentum. The rotating updraft narrows as it's squeezed by that precip-induced downdraft. Okay, so as the downdraft is enhanced because the precipitation is falling, so it's dragging air with it. So the downdraft is enhanced. The rotating updraft narrows. Well, why does it do that? Because angular momentum is conserved, and it's bringing in toward the axis stronger air. And as it nears the air with stronger rotation, as it's doing so, the air is rotating faster. They cause then the mesocyclone to contract and descend to the ground in a roughly cyclostrophically balanced manner. Okay, so if you saw a movie of this thing, you would see the vortex as the rain descends here. As this rain curtain comes down, you start to see the vertical velocity pick up. There you see it increase. You start to see the horizontal winds increase, and notice how the intensity. Here's the max up here. Later on in time, the max is descended. Okay, so essentially, you look at the V phi. Here's the center of rotation. Now the center of rotation is lowered. So essentially, it's saying you get a lowering effect of the rotation due to essentially the hook echo of rain falling at the updraft downdraft interface. So they cause the mesocyclone to contract and descend. And as the max and tangential velocity hits the ground, some of it flows radially inward, and a new max forms below and moves inward. So it's not a perfect model, but essentially it shows how just this passive effect of dragging air down, conservation of angular momentum, causes this spin up and this descent of the ground. So the near ground vortex, as it says, becomes the most intense, rapidly intensifying into the tornado. And again, the reason why he did this experiment the way he did was that observations show that there's very little temperature gradient underneath at the ground in the mesocyclone area and in the riffling downdraft. And this is the so-called mobile mesonets that do these transects below the storm. Very, very valuable observations that showed the temperature didn't change much. And that was a huge surprise because we thought that there were baroclinic effects there. Okay, so I wish I were there to answer any questions you might have about this. I suspect there are some. We have about 15 minutes left. So let me segue a little bit here into cyclic tornado genesis. Kind of a favorite topic of mine because one of my doctoral students did his dissertation on this topic, and we've published papers on it. So this leftmost figure here is from Don Burgess, who's now retired, but he's still at Sims. Basically, we notice, and Fujita noticed this as well, that you tend to get so-called tornado families forming a lot of times. You see this thing here, this is T1, that means the first tornado, T2 is the second tornado, T3 is the third tornado. Essentially from the same storm, but with different mesocyclones. And so before Doppler radar, we'd look at these things and say, well, it was a family of tornadoes. But then when we really started looking at these things with Doppler radar and were able to look at the structure of the storm, we realized that what was happening here was you get an initial mesocyclone that you see here on the left. The low indicates a mesocyclone. It starts to put out a tornado here as the mesocyclone is mature. And here's this big black line here indicates the tornado track on the ground. And you see here that this old mesocyclone becomes rain-wrapped. The rear flank downdraft pushes out ahead like we saw before. And this old mesocyclone then tends to occlude back in the cold air. And the tornado stops, okay, because it's occluding, the rain is falling, the vortex is getting squashed. We don't want that for a vortex to be strong. We want it to be stretched. It's squashed and it eventually dies. But the convergence associated with the rear flank downdraft push creates a second mesocyclone to the east of it. So this old mesocyclone eventually curves here to the left and dies. And this new mesocyclone essentially repeats the same process as the old one and puts out a new tornado downstream. And that's how you get this succession of tornadoes. Well, one of my students, Ed Adlerman, did numerical simulations at very, very high resolution because we wanted to understand the physics behind cyclic tornadogenesis. Why do some storms cycle and why do some storms not cycle? And is there a parameter space that we could map, kind of like the Bulk-Richardson number, that would be helpful to forecasters to say, okay, in these cases, I know a storm is going to tend to cycle and maybe produce multiple tornadoes in families versus not. So what we're looking at here is essentially the reflectivity field of a numerical simulation in horizontal cross-section. It's a 3D simulation, very, very high resolution. And this A here indicates the tip of the hook echo where basically a tornado cyclone is occurring. So here's the forward flank downdraft, classic supercell storm. Here's a hook echo. I can't quite read the dimensions. I think this box is about, 20 or 30 kilometers on a side. This is 5,100 seconds into the simulation. So these are 300 seconds apart. These are 5-minute snapshots. So here's the initial mesocyclone. Notice how it kind of breaks off here. There's A. There's A. Now we're moving with the storm. Okay, we're in a box moving along with the storm. So this thing, notice how the rain now is sort of wrapping around the mesocyclone, and a new spin-up occurs off to the northeast in this case. The old mesocyclone is here, the new one is here, so now there are two present. A is dying, B is formed, and now A has pretty much died off. And notice the rotation, the hook echo is starting to form in B. A little bit later on in time, A is completely gone, and notice we have a brand new mesocyclone, but it's within the same supercell storm. We haven't created a new storm, we've only created a new mesocyclone slightly downstream due to the strong convergence along the gust front, which isn't shown here. I'm only showing you the reflectivity. And then B eventually forms a strong tornadic mesocyclone. Again, 5-minute intervals. So this is 5, 10, 15, 20, 25, 30, about 25 minutes. We go from one mesocyclone maybe in a half an hour to the second one. Now, in reality, I think the storms tend to cycle faster than this. They tend to cycle maybe at 15 to 20-minute intervals. And what's very interesting from a personal point of view, when we were chasing storms back in the 70s and 80s, we would see this phase in here where the mesocyclone was dying out, okay? And we chase it. Suppose it didn't produce a tornado. We'd turn around in our car and drive to another storm. And this happened in one time in particular in the Texas Panhandle. So we're blasting down the highway to the next storm, and we look around behind us, 15 minutes later, and the storm has spun up a beautiful, huge mesocyclone producing a tornado. We're like, what in the world's going on? Now, the mesocyclone was dying. It clearly was dying. What was happening was it was producing a new mesocyclone, spinning up a second mesocyclone, not the old one, and the storm was cycling, and we didn't realize that. So, this was observed, but we didn't understand why it happened. Now, I've got a great movie here, and it's actually linked to the class website, I believe. So I would urge you to go to the assignments page where it has all the reading and stuff and watch this movie. It shows what I just showed you in animation. It's very, very impressive when you see this. It's a very, very cool thing to watch. Okay, so that is the end of our discussion of non-supercell tornadoes. Now, I realized just now that, as I mentioned, this issue of a parameter space, that in our journal article, Ed and I did create a parameter space for looking at cyclic versus non-cyclic tornadic storms, and I, for some reason, didn't put it in the slides here. So I'm going to do that, and I'll come back and revisit that next class period, okay? Because I do want to show you that, because there is a space, kind of like you saw with the Bulk-Richards number, it's more complicated, that tries to distinguish, excuse me, cycling storms from, pardon me, from those that do not cycle, okay? All right, so let's turn attention now to the so-called Type 2 tornadoes, which are the non-supercell tornadoes, and this is kind of a neat picture that shows you have clearly what is not a supercell storm, but you have 3 tornadoes coming out of it at one time. Okay, now this is, maybe some people dream about this. Very difficult to forecast this, but these are non-supercell storms. In fact, in this guy over here, you see the condensation funnel kind of becomes hollowed out. This is debris, probably on the ground debris. This is condensation, most likely, and maybe some debris. And so there's a variety of ways in which these tornadoes can form. So let's take a look at that. Let's take a look at the role of the downdraft when vertical vorticity is present initially at ground. You say, well, how could vorticity be present initially at the ground? Well, it can be. There can be cases where, for example, you have convergence lines or whatever, that there is vertical vorticity. Of course, it's always present at the ground in the form of the Coriolis force, but it's much weaker than just due to, say, for example, a convergence line that is sitting there from a previous day's storm or something like that. So suppose that we have no low-level baroclinic generation, no gust front, no nothing. Let's assume that we have vorticity present at the ground. Okay, we put a cloud in that environment. Okay, what's it going to do? Well, we get low-level convergence, right? Because if we have a cloud forming, then there's updraft. There's got to be mass continuity. So it's bringing these vortex lines together with time. And eventually, you're going to increase the vorticity simply by advection. Okay, so we're advecting vorticity from one location to another. And when those vortex lines coalesce, and as they do, then you will generate vorticity that is stronger than what you had initially, simply due to convergence. And there's some stretching going on here, but initially it's simply advection. Okay, so roll of the downdraft when vertical vorticity is present initially at ground. Okay, so here we are continuing this picture. On the left it says rotation increases as vortex lines are converged beneath the updraft. So as I said, this part here is advection, bringing the vorticity together. You get intensified vorticity now. You get convergence because you have low-level convergence, okay, beneath the updraft. And therefore, as it says here, the spacing between the vortex lines is inversely proportional to vorticity magnitude. In other words, the smaller the spacing, the larger the vorticity. Okay, and that has to do with what's called the strength of a vortex, which is the cross-sectional area of the vortex times the vorticity. So if the cross-sectional area goes down, there are more vortex lines in there, the vorticity will increase in intensity. And so you're spinning this up initially by advection and then by stretching. No tilting involved and no baroclinic generation at all. The vorticity is already present. Okay, so that's one way to do it. Now, where does this exist? Well, for example, if you have a convergence line, okay, that might be an outflow boundary from the previous day or something where there's weak low-level convergence, you could get spin up of vorticity. You could get vertical vorticity already existing along that convergence line. Okay, you can clearly see there's shear vorticity already at the ground. And if you put updrafts above that, you put clouds above that, it's going to take that vorticity, it's going to advect the vortex lines together, and when the cloud gets vigorous enough, that will stretch the vortex and could produce a weak non-supercell tornado. Okay, so there's a kind of a schematic of what we saw earlier in 2 dimensions. Okay, here's another example of that, of so-called land spouts in a baroclinic zone. You see these oftentimes out near Denver, east of Denver. You see these very vigorous clouds. You see convergence lines out there. There's something called the Denver convergence zone, the Denver cyclone. You see convergence lines out there a lot, and they have shear along them. Well, shear, of course, is vorticity. So you have pre-existing vertical vorticity. And if you get a baroclinic zone here, a gust front interacting with it, like we saw with the horizontal convective rolls, that will create strong convergence in the presence of vorticity, strong lifting along the gust front, and you could then generate vertical vorticity by stretching that is strong enough to produce, for example, what's called a land spout. And so what's needed for this is, again, a pre-existing source of vertical vorticity, which in this case is a convergence line, and then in this case something to promote and initiate the lifting other than daytime heating, and that would be this baroclinic zone. Okay, and then Once you get downdrafts here, then you can get tilting of the horizontally generated baroclinic vorticity here, which can intensify this, and you can spin up maybe perhaps an even stronger tornado. And there's an example of a gustnado right here. This is a picture from your book. There's a gustnado. Right there you can see the debris on the ground. It's very weak, and it's at the leading edge of the storm. So some people kind of freak out when they see gust fronts. They're not always innocuous. Sometimes there are intense vortices there, like you see here, but most of the time they're not super strong. Okay, so I'm going to stop there. We have about 5 minutes left, and I'm assuming you maybe needed a few minutes to get the video going. So we'll pick it up here next time, and that will be the last day of class. And again, please remember to do the class evaluation. And if we have time on Thursday in class, I'll give you some time in class to do it. So bring your laptops with you to fill it out. And also be thinking about the day for the exam review. And I'll send out an email here in just a minute, just reminding you of that as well and checking your calendars. So I will see you on Thursday.